So if we have some complex number set, which generally can be written as R in E in I alpha, then this R is equal to the absolute value of set, and this alpha is equal to the argument value of set. This may not be the principal argument, it can be multiple valued. So if we now have some particular examples of such number, call them set 1 and set 2, written in this way, then we can multiply these two complex numbers with each other, and we obtain this. We can rearrange because the factors are rearrangeable, and we obtain a new R for the product. So let's call the multiplum of these two complex numbers for complex number set, which have absolute value R, which is this product, and we see that this can be multiplied with the exponential function of I multiplied with the sum of these two argument values. So what we see here is that when alpha 1 is the argument value of set 1 and alpha 2 is the argument value of set 2, then this new alpha value for the product is just which is the argument value of set 1 and set 2, can be written as a sum of these two alpha values. So let's illustrate this. We have these two complex numbers set 1 and set 2, which has the argument value alpha 1 and alpha 2 respectively. So when we have the product called set here, then the argument value of this set is equal to the sum of these two alpha values. So here we have that the argument value of set 1 can be written in this way, is equal to the argument value of set 1 and set 2, sorry, it should be 2 here, is equal to the argument value of set 1 plus argument value of set 2. When we are replacing it with the principal argument value, it's not always the case. So this does not hold generally, and let's give an example of this. If set 1 is equal to minus 1, then the argument value, let's just illustrate this set 1 here, is simply this vector at the real line pointing in this direction, which has the argument value, principal argument value pi. Here is set 2 equal to I, which is pointing in this direction, and the argument value of this, the principal argument value, is pi over 2. So in this case, when we are multiplying these two complex numbers with each other, we get 1 multiplied with this minus 1 multiplied with I equal to minus I, and the principal argument of minus I is just minus pi over 2. But what we see here is that the argument value of set 1 is pi. The principal argument of set 1 is pi, and the principal argument of set 2 is pi over 2, so the sum of them are 3 over 2 multiplied with pi, which is not the same. So here we have an example where we cannot use this formula generally for the principal value, principal argument of complex numbers. Here we have another formula which is somehow important in many cases. It's very easy to derive if we have a complex number of polar form like this. We just write set in the power of n, then we of course obtain this guy, and if, for example, r is equal to 1, we obtain that set in the power of n is just equal to e in the power of I alpha n. So in this case, set is just the exponential function of I alpha. So noting that the exponential function of I multiplied with some general angle is equal to cosine plus I sine, then we obtain by using the above formula, because this is just this cosine plus I sine in the power of n, and by the above formula here we have that this must be equal to cosine n alpha plus I sine n alpha. So here is just some exercise to use this formula. Write this complex number, the square root of 3 plus I in the power of 7 in rectangular form. And the rectangular form is in this form. So how can we do this in the easiest way? Well, we write this guy in polar form first, like this, and then it's easy to write this polar form in the power of 7. So then we have 2 in the power of 7 multiplied with the exponential function in I multiplied with pi over 6 multiplied with 7, and this is equal to, we know that by the Euler formula that this is equal to cosine of 7 pi over 6 plus the sine. Here you should multiply with the imaginary unit I also. Sorry, I haven't done this, but you see what's missing. So the sine of 7 pi over 6. So what we are getting here is that this expression is just minus this. It's rather easy to see that this is minus the square root of 3 over 2 minus I multiplied with 1 over 2, which is equal to this expression. Okay, let's turn to some other example. Why or some other aspect of the previous example. Y is the square root of 3 plus I equal to 2 multiplied with the exponential function of I multiplied with pi over 6. Well, you see here, if you take the imaginary part and divide it with the real part, you obtain 1 over the square root of 3. And this the alpha value making this the tangent equal to this guy is just 30 degrees, which is the same as pi over 6. And the absolute value is very simple to see because you use the square root of this, the square of this guy plus the square of the imaginary part 1, and you taking the square of this, you obtain 2. So that's the reason why we obtain this.